Okay, hello everyone. So this is the first seminar of the term, and Igor Sikora from University of Warwick is going to tell us about ROC2 graded coefficients of C2 Eilenberg-MacLane spectra. So Igor, you can go ahead.
Thank you. And firstly, of course, I wanted to thank Jihan for inviting me to give this talk. Okay, yeah, so let's get started. As already said, I'm going to talk about ROC2 graded coefficients of C2 Eilenberg-MacLane spectra. So let's start with some overview of the problem which we are going to discuss. So it is, well, a trivial statement that in the non-equivariant topology, computing the singular homology of a point with coefficients in some abelian group or a ring R is quite simple because we just need to take a look on the dimension axiom. And we know that this homology is concentrated in degree 0. So it means in particular that it is 0 everywhere else. So the problem is that it's not so easy in the equivariant world. What do I mean by not so easy? So let's compare homology of a point, non-equivariant homology of a point with coefficients in F2. So no surprise, it is concentrated in degree 0. So here we have a kind of symbolic depiction. And on the right-hand side, we have a homology of a point with well, equivariant analog of F2, which is constant F2 Mackey functor. So this is homology over taken over the cyclic group of order 2. So what we can see here, first of all, this homology is kind of two-dimensional. It is graded over the ring of representations. So I will make sense of it a little bit later. Again, if we are following the gradation over trivial representations, we see that it is concentrated in degree 0, but outside this comfortable world of a trivial representation, it's not so easy because we can see a lot of non-zero entries in different degrees. So the computations of this kind, the computations of the homology of a point with different Mackey functors will be what will be the goal of this talk. So as I said, the goal of this talk will be to describe a method for computations of the C2 equivariant homology of a point. And we require this method to satisfy two properties. Firstly, we want it to make the computations feasible. And also, we would like it to unveil as much structure as possible. So our object of study is C2 equivariant ordinary homology of a point. But instead, we are going to discuss coefficients of C2 Eilenberg-MacLane spectra. These are really the same thing, but calling it as coefficients of C2 Eilenberg-MacLane spectra allows us to use different methods from equivariant stable homotopy theory. And the method of these computations will be so-called the Tate method. So this is the method based on the Tate diagram as developed by Greenlees and May. So firstly, let's discuss what is Bredon homology. I will not give here a full definition because it takes too much time. Instead, I just want to give a couple of properties of Bredon homology, how we should think about it. So let's start with G a finite group. In general, what I'm going to discuss here will mostly work for compactly groups, but I just want to be as safe as possible, so I'm sticking to finite groups. So Bredon homology is first of all ordinary equivariant homology theory in the sense that it satisfies equivariant versions of Eilenberg-MacLane, Eilenberg-Steenrod axioms. In particular, it satisfies the dimension axioms, which means that if we take the gradation over trivial representations, it is concentrated in degree 0. The second property is that it takes Mackey functors as coefficients. So this is what makes computations kind of problematic because Mackey functors are, rather than single abelian groups, these are diagrams of abelian groups connected by some maps, and this is what makes computations harder. And the second property which makes computations harder is that it is greater over the ring of G representations denoted by ROG. So small aside, what is ROG? The usual definition is as follows, that we take ROG twiddle to be the semi-ring of isomorphism classes of real G representations with a direct sum and tensor product taken as the semi-ring operation, and then we perform the gradient deconstruction on the ROG twiddle in the sense that we are just adding additive inverses. So example is that the ring, the representation of the ring of the cyclic group of a prime order is given as this polynomial ring divided by x to the power p minus 1. In particular, we can see that arrow of C2 is two-dimensional and generated by the class of the trivial representation, and this is the class of real sign representation. There is a small problem with such a notion of ROG, and the problem is that if we define ROG as isomorphism classes of real G representations, it is hard to simultaneously keep track of signs. So the way of overcoming this problem is that we consider ROG to be a free abelian group, well, the free abelian group on irreducible G representations. So for us, ROG will be, sorry, it really should be the free abelian group on irreducible G representations. It doesn't change a lot because still for C2 it is two-dimensional and generated by the class of one trivial representation and the class of the sign representation. So coming back to the Bredon homology, this is represented by the equivariant Eilenberg-MacLane spectra, denoted similarly to the non-equivariant topology by HM. So here what I have written is the dimension axiom, more or less, which means that the G homotopic groups of the Eilenberg-MacLane spectrum are really concentrated in degree 0. But if we consider them graded over trivial representations, because if we leave the trivial representations, we obtain the picture which we seen on the in the overview. And how these homotopic groups of the Eilenberg-MacLane spectrum are connected to the ROG graded homology of a point? Well, by equality sign. These are really the same things. And here, the important thing is that this 5-pointed star is what indicates that we are grading over ROG. So what do we mean ROG grading in the case of homotopic groups? We mean that V homotopic group, G homotopic group, is the set of G homotopic classes from the representation sphere of V to HM. And for those of you who haven't heard about representation spheres, this is a one-point compactification. Of V. So our goal in this talk will be to compute these ROG graded homotopic groups, which will denote in shorter form like this. And these guys are called coefficients of IHM. And actually, we are doing a little bit less. We are doing this only over C2. So the second thing which I should discuss here are what are C2 Mackey functors. Yet again, I will not give here the full definition of the Mackey functor. Rather, I will just discuss them over C2. Because over C2, they have particularly simple structure. Because C2 Mackey functor consists of two abelian groups. one on the C2 level and one on the E level. Both abelian groups have C2 action, but the abelian group on the C2 level needs to have trivial action of C2. So let's write it. And the bottom one has possibly non-trivial action. And these two groups are connected by two C2 equivariant maps. The first map going from the bottom level to the top level is called the transfer. And the map going from the C2 level to E level is the restriction. And these two maps are further connected by this formula over here. So this formula is a so-called Mackey condition, and it just says that if I take the class from the E level and I go through the transfer and through the restriction, what I will need to get is x multiplied by 1 plus gamma, where gamma is the generator of C2. So yeah, rather simple structure, but well, not so simple as single abelian group. A couple of examples of Mackey functors over C2. The first one is constant Mackey functor on Z, so on the integers. So it consists of integers with trivial C2 action on both levels. Then the restriction is given by the identity. And forcefully, we need to have that the transfer is given by the multiplication by 2. The second example is the constant Mackey functor on F2. Similarly, we have F2 with a trivial C2 action on both levels. So again, we don't have much more actions on F2 of C2. The restriction is given by the identity. And here again, the transfer forcefully is multiplication by 2, but multiplication by 2 in characteristic 2 is just 0. The crucial example for us will be the Burnside Mackey functor, which is given as presented on the bottom level. It has the integers with trivial action, and on the upper level, I gave here the computational form, but really this is the Burnside ring of C2, and here the omega is the class of the set C2 divided by E in the Burnside ring. The transfer is given by multiplication by omega, and the restriction is given by sending 1 to 1 and omega to 2. So if we wanted to check the Mackey condition, it works 1 times omega is omega, and then omega goes to 2, so works. And the last example given over here, I just wanted to give an example of Mackey functor which doesn't have a trivial action on the bottom level. So this is fixed points Mackey functor of Z twiddle, and Z twiddle are integers, but with the action given by the sign. So the generator of C2 acts by multiplying by -1. So on the bottom level, we have Z twiddle, and on the top level, we have 0. So forcefully, of course, transfer and the restriction are 0. Really, what we are going to compute for these coefficients are 3 levels of structure. So firstly, as usual, we are computing the structure of an abelian group. So the first level of structure of these coefficients is ROC2 graded abelian group. But we have also second level, which comes from the fact that every Mackey functor is a module over the Burnside Mackey functor. So the category of Mackey functors actually has a symmetric monoidal product, which is called the box product. And the unit of this box product is the Burnside Mackey functor. And this multiplication carries over to the category of spectra. So this means that every Eilenberg-MacLane spectrum is a module over the Burnside Eilenberg-MacLane spectrum. And therefore, the coefficients of every Eilenberg-MacLane spectrum are the coefficients over the ROC2 graded coefficients of the Burnside Eilenberg-MacLane spectrum. So this is the second level of structure. And the third level of structure is that if our Mackey functor M is itself a ring with respect to the box product, so this means this is called that M is a green functor, then its Eilenberg-MacLane spectrum is itself a C2 ring spectrum, and therefore its coefficients are ROC2 graded rings. So this is the third level of structure which we are going to discuss. So let me give some motivation for this project. Why do we actually care? So first motivation, I think it is a little bit self-explanatory why it is important to compute the homology of a point, because it is actually the simplest topological space, simplest non-empty topological space. So it would be rather good if we knew the homology of a point. But let's extend this motivation a little bit. So the coefficients of Eilenberg-MacLane spectra, or the homology of a point, is really fundamental in computations of ROG-graded homology of other spaces. Similarly, as in the non-equivariant world, if we want to compute homology of any space, firstly, we need to know the coefficients of the homology theory. So the similar case is here. And the second thing why we would care about coefficients of Eilenberg-MacLane spectra are that they are basic objects in the category of G spectra. So we need to understand the homotopic groups, the G homotopic groups of them for other computations. So in the equivariant stable homotopy theory, a part of the Tate diagram, there is another big way of computing things, big method, which is called the slice spectral sequence. So this is developed by Hill, Hopkins, and Ravenel, and used in their very famous paper on the non-existence of the element of curvature invariant 1. And actually, Eilenberg-MacLane spectra appear in the computations for the slice spectral sequence because they are, I think, -1 slices for every spectrum. So really, we need to know the homotopy of Eilenberg-MacLane spectra to perform other computations. And a little bit of history of these computations over C2. So the first computations of these coefficients were done by Stonk in his legendary unpublished work. So because it is unpublished, it's kind of hard to find it, but everyone in the field is referring to this unpublished work, so I'm giving this reference here too. In 1988, Lewis computed the coefficients of the Burnside Mackey functor A. So just a remark, if I'm talking about coefficients of the Mackey functor and coefficients of the Eilenberg-MacLane spectrum associated to the Mackey functor, these are really the same thing. So sorry if I'm sometimes doing this abbreviation. The most general answer was given by Fairland in his PhD thesis in 1999, and it appears also in Fairland-Lewis article from 2004, where they give the ROC2 graded abelian group structure of the coefficients of Eilenberg-MacLane spectra for every Mackey functor, and they also give the structure of module over the Burnside ring. Other explicit computations are Caruso in 1999, who computed the coefficients of the Eilenberg-MacLane spectrum associated to the constant Mackey functor on F2. So here, I'm not sure who was the first, whether it was Caruso or Ferland, so I'm giving them in somehow random order. And other computation was done by Dagger in 2005. He gave an explicit computations of the coefficients of the Eilenberg-MacLane spectrum associated to the constant Mackey functor on the integers. So one might ask, what is the point of this talk if or of this project if these coefficients are already computed? So the answer is that firstly, we are going to reprove these Ferland and Ferland-Lewis results by different method. We are going to extend a little bit these results because we are going to say something about the multiplicative structure, about the ring structure. And thirdly, somehow the secret goal of this talk is advertising the Tate method as a good method of performing such calculations.
Okay, so what are the examples of Mackey functors other than constant one and this A, the Burnside, that are of interest?
Yeah, so that's a good question. Actually, usually the constant Mackey functors are used, and the Burnside Mackey functor because it is important. But for example, I will give a little bit later example of a different Mackey functor. So it is called B. So this is a norm from E to C2 of F2. This is Mackey functor which looks as follows: Z mod 4, Z2. Here we have 1. Here we have multiplication by 2. So this is non-constant Mackey functor, and it was used by Mike Hill in computations of the Bredon homology of signed loop spaces. But really, I think that doing equivariant computations is hard. So this is why people are firstly trying to sort out the simple examples like the constant Mackey functors. And then possibly we can discuss other examples. Okay. Are there any other questions? No. Okay. So let's proceed. Before we are going to discuss the Tate method, let's sort out the easy part. The easy part of these coefficients is the part which is graded over sign multiplicities of the sign representation. So let A be the element of minus sigma C2 homotopy group of the sphere spectrum. And this element is given by the inclusion S0, S0 to S sigma. So just a remark, this is the same thing as pi C2 0 of S sigma. This class, A, is also known as the Euler class. And we can describe the multiplication by A in the coefficients of any Eilenberg-MacLane spectrum by the following properties. So it is a monomorphism if x minus 1 is equal to y. It is an epimorphism if x is equal to minus y, and an isomorphism otherwise. Really, the message here is that it is an isomorphism unless it leaves or hits the anti-diagonal. So what we are going to see is that the coefficients have this kind of vertical periodicity. which can be broken at only one point, well, at only one line, which is the anti-diagonal x equals minus y. So in particular, we can compute that the groups graded over the multiplicities of the sign representation are given as follows: that if y is bigger than 0, then it is the kernel of the restriction. If y is smaller than 0, it is the co-kernel of the transfer. And if y is equal to 0, then it is the C2 level of our Mackey functor. And these computations just comes from the cofiber sequence. So we take C2 with additional base point. So this is C2 with added base point. We send it in the somehow trivial way to S0. So base point is going to the base point, and everything else is going to the other point. And this, the cofiber of homotopic cofiber of this sequence is a sigma. So sorry, this is, maybe I will draw it a little bit bigger. This looks as follows. So this is just one sphere with the reflection given by the axis symmetry. And applying, smashing this cofiber sequence with HM, or applying C2 homotopy maps from this cofiber sequence to HM exhibits the transfer and the restriction in our Mackey functor. So let's look at the picture. On the left, we have a reminder how our Mackey functor looks like. So again, on the 0 level, we have the C2 level of our Mackey functor in the 0th degree. Below 0 on this vertical axis, we'll always have the co-kernel of the transfer. And above 0, we have the kernel of the restriction. By, yeah. Here, what we can see is a first instance of this vertical periodicity, which I was talking about, because really what we need to compute is the minus sigma degree and the sigma degree, because everything else will follow from the A periodicity, which goes in the vertical direction. So the easy part of the computations is sorted. So do you have any questions about it?
So the A periodicity, what was that map? Could you just go back to
Yes.
Couple slides back where you define
so
that? Oh, okay, so it's a shift in the sigma direction. Yeah. Okay.
Going down.
Okay. So is it related to the HA module structure, or is it something else?
It is actually related to HA module structure, because the class of A, that we can describe the ring structure of the Burnside Mackey functor, of the coefficients of the Burnside Mackey functor, using two classes, A and U. So I will talk about it a little bit later. And then the element A appearing in the Burnside Mackey functor, the coefficients of the Burnside Mackey functor, acts on the coefficients of every other Eilenberg-MacLane spectrum. So really, this is something which comes from the HA module structure. Yes.
Okay, thanks.
So let's discuss the method which we are going to use. Okay. And let's discuss the Tate diagram and the Tate square. So let G for now be a compact Lie group, and let EG be, as usual, the free contractible G space. And we define the following cofiber sequence. So here we have EG plus with added base point, S0, Yeah, so we are sending base point to the base point and everything else to the other point of S naught. And the cofiber, homotopy cofiber of this sequence is what will be denoted by EG tilde. So this cofiber sequence is what is known as the isotropy separation sequence. So let's start with a G spectrum X. There is a map epsilon, which goes from X to the function spectrum from EG plus to X. And this map is really induced by the first map in our isotropy separation sequence, because X is the same thing as the function spectrum from S naught to X. So we are just applying function spectrum to X to the first map in the isotropy separation sequence. Then we are smashing epsilon with, again, with the isotropy separation sequence. So we obtain the following diagram. So, oh, sorry. On the top level, over here, we have X smashed with the isotropy separation sequence. And on the bottom level, we have F EG plus to X smashed with the isotropy separation sequence. And these are connected here by epsilon and here by maps by epsilon smashed with the isotropy separation sequence. So first fact about this diagram is that the map on the left, EG plus, sorry, it should be epsilon here. The map EG plus smash epsilon is a G equivalence. And this comes from the fact that epsilon is a non-equivariant equivalence. So after smashing with EG plus, it becomes a G equivalence. And hence we have that the right-hand side square over here is a homotopy pullback. So let's give a couple of names to the spectra which appear in this diagram. Firstly, X subscript H is the spectrum appearing in the top left corner. So this is EG plus smash X, and this is known as the free G spectrum associated to X. Secondly, X superscript H is the function spectrum from EG plus to X, and this is known as the Borel completion of X. Thirdly, by X was superscript phi, we will denote EG twiddle smashed with X. So this is the singular G spectrum associated to X. And finally, the Tate spectrum associated to X is defined as EG twiddle smashed with function spectrum from EG plus to X. In other words, the Tate spectrum is EG twiddle smashed with the Borel completion. So after renaming the entries, we get the following diagram as given here. So this diagram is known as the Tate diagram. Here we have an equivalence. The right-hand side square of this diagram is known as the Tate square, and it has the property of being a homotopy pullback. And moreover, a very nice and very important property is that of the Tate square is that if X is a ring spectrum, then the Tate square is actually a homotopy pullback of ring G spectra. And the same thing holds for module spectra. So if we have a ring C2 spectrum or ring G spectrum R, then and X is a module over R, then the Tate square becomes a homotopy pullback of modules over R. So let's proceed to the strategy of how we are going to perform these calculations using the Tate diagram. So here is the Tate diagram so that we remember how it looks like. And let M be a C2 Mackey functor. Of course, now we are coming back to the world of C2 because it is nice and safe here. First step will be to compute the coefficients of the free spectrum and the Borel completion of HM. So first step is to compute these two guys in the bottom level. And we can do it by homotopy fixed points and homotopy orbit spectral sequences. So we have spectral sequences. That means that we can compute something, more or less. The second step will be to derive the coefficients of the Tate spectrum associated to HM from the bottom sequence in the Tate diagram. So we can do it in two ways. Firstly, we can just use the fact that the bottom row is a cofiber sequence, but alternatively, we can just invert A in the coefficients of the Borel completion. And why is that? This is because the Tate spectrum is defined as the Borel completion smashed with easy Twiddle. And easy Twiddle have a very nice model, which is representation sphere of infinite copies of sigma. In particular, such a representation sphere may be seen as a colimit of a sequence of representation spheres associated to I sigma. So we have that the coefficients of the Tate spectrum are actually colimit of this sequence. And we know that colimit of this sequence means just inverting the class A. So this was the second step. The third step will be inferring the coefficients of the singular C2 spectrum associated to HM. For this, we will use the following lemma, that if X is a C2 spectrum which is non-equivariantly connective, then if this map over here is a connective cover on the level of categorical fixed points, then so is this map over here. So this is the third step. And the fourth step is that we compute HMC2, the coefficients of ROC2 graded coefficients of our starting Eilenberg-MacLane spectrum. So references for this method are Greenlees and May, the book Generalized State Cohomology, and also an article by John, 4 approaches to cohomology theories with reality, where he's using this method to compute the coefficients of the Eilenberg-MacLane spectrum associated to the constant Mackey functor on integers, and also to the K-theory with reality. So he's computing the ROC2 graded coefficients of K-theory with the reality. So let's see that this method, as presented, it might sound complicated, but really it is somehow algorithmic approach with very easy steps. Because step 1 is we need to compute coefficients of this. Step 2, we need to compute the coefficients of the Tate spectrum. Then we are computing the coefficients of the singular spectrum associated to HM, and our grand finale is computing the coefficients of HM. How much time do I have left? 10 minutes. Right?
But you started late, I guess.
Okay.
Yeah, I can. Yeah, I think you can take 15.
Okay.
Exactly, if you want.
So we will do the main point of this talk is to do a toy case of these computations. So I will proceed to this. But firstly, I just need to tell you how these spectral sequences work. So recall that the free spectrum associated to HM and the Borel completion are defined as given here. And in both cases, there appear a space, the space EC2 plus. And again, we have a very convenient model of this space. This space is a unit sphere in the infinite copies of sigma. And this has filtration by skeleton, as here. So these are unit spheres in sigma, in 2 sigma, in 3 sigma, and so on and so forth. And consequently, we obtain a filtration on the free spectrum and on the Borel completion. If we have a filtration on a spectrum, we obtain a spectral sequence. So these spectral sequences, what is important for us here is that, well, of course, it is important that they converge where we want them to converge, but they take as entry a group homology and cohomology of C2 with coefficients in non-equivariant homotopic groups of our Eilenberg-MacLane spectrum, treated as the C2 module. So these homotopic groups are just homotopic groups of a restriction of this Eilenberg-MacLane spectrum. So this is a good information because homology and cohomology of C2, group cohomology and homology of C2 are actually quite well understood. And moreover, these spectral sequences can be formed to be tree-graded. So we can use them to compute ROC2 graded homotopic groups of Eilenberg-MacLane spectra. So here, how we do it, here we have the definition of what is the homotopy group of IHM, IHC2. I will discuss this way only for the Borel completion. It works more or less the same for the free spectrum. By classical adjunctions, we have this isomorphism. And then we see that this is really the same thing as non-equivariant homotopy groups of C2 fixed points of the Borel completion of this function spectrum over here. This function spectrum over here. So we can make the homotopy orbits. Sorry, this is not homotopy orbits. This is homotopy fixed points. Homotopy fixed point spectral sequence tree-graded. Here we have the third grading over Y. So this is kind of twisted degree, and it appears over here. Again, really how we should think about this tree gradation is that this is just a family of spectral sequences indexed over Y. Because really all differentials live on one spectral sequence corresponding to one value of Y. This tree gradation is important when we are talking about the multiplicative structure. And yeah, by the similar argument, we can get that the tree-graded homotopy orbits spectral sequence has this form. So let's see how this method works on a toy case, and the toy case will be IGF2. So the constant Mackey functor on F2, which I discussed in the overview. So firstly, in the first step, we are computing the bottom row of the Tate diagram using the homotopy fixed point spectral sequence and the homotopy orbit spectral sequence. But for this particular spectrum, the coefficients appearing in the group homology are incredibly simple because these are just F2. So we get that the homotopy, the coefficients of the Borel completion and the coefficients of the free spectrum looks as on these pictures. And here we see shifted copies of the group cohomology of C2 with coefficients in F2. And same goes here for the group homology. The second step was to derive the coefficients of the Tate spectrum. So again, we can do it in a twofold way. We can glue the coefficients of the Borel completion and the free spectrum along the antidiagonal, or we can just invert A and A on this A always goes this way. So after we inverted A, so multiplication by A is really over here. After we inverted A, we obtained the plane full of dots. And the step 3 was to compute the coefficients of the singular spectrum associated to IGF2. So here we are using the connective cover lemma, which in practice just says that take the Tate spectrum, the coefficients of the Tate spectrum, and cut everything which is below the fixed degree 0. Okay, so these were steps 1, 2, and 3. So we have computed everything in the diagram apart of what is of our main interest, so the coefficients of IHF2 C2 star. So I'm not really sure, to be honest here, if this diagram is a pullback of anything, but actually simply by just chasing the diagrams and using cofiber sequences, we can get the answer which I gave you in the overview, which is as expected, as given here. So here we have 1, here we have sigma. Okay, so these are coefficients of IHF2. Another example, sorry, before I will proceed to this example, do you have any questions about it?
Sorry, what was the connective cover lemma that you mentioned? I think you mentioned it at some point, but what did it give us?
Yes, so the connective cover lemma was that if X is a non-equivariantly connected spectrum, then let's look at on the Tate diagram over here. X, well, actually, let's just take a look on the Tate square. So here we have the Tate square, XH, XT, X phi, and the connective cover lemma says that if on the level of the C2 fixed points, this is a connective cover, then this is a connective cover as well. Okay.
Okay.
And we can use this lemma here because IHM is somehow trivially non-equivalently connective spectrum. And because it doesn't have anything below 0 on the in the trivial on the part graded over trivial representations, it doesn't have anything below the 0 degree. Then this map on the left is a connective cover. Then also the map on the right is the connective cover. So really what we need to do to compute the coefficients of the singular spectrum is to cut everything from the Tate spectrum below the twisted degree 0. Sorry, below the fixed degree 0.
Okay, thank you.
So let me give you a general answer for this. So general answer is as given here. Let me remind you that it was given by proven by Ferland, and I reproved it using the Tate method. We can see a lot of things here, but really the message is that the guys in degree 0 in the fixed degree 0 are submodules of the C2 level of the Mackey functor. In degree -1 and 1 are submodules or subquotients of degrees fixed degrees -1 and 1. And the parts over here are related to, very closely related to group homology and cohomology of C2 with coefficients in the E level of our Mackey functor. What we can also see here is that on the right half plane, we have everything is 0 above the antidiagonal, and on the left half plane, everything is 0 below the antidiagonal. And this is pattern which is also in all coefficients of all Eilenberg-MacLane spectra. Okay. The other example is the Burnside Mackey functor. So we can see a couple of differences from the coefficients of IGF2. Firstly, rather than having just one group appearing in all entries, we have 3 different groups. Secondly, we have things, non-zero things on the vertical axis over 0. And also we can see here kind of regular pattern that in the 4th quadrant, we have non-zero columns only in even fixed degrees. Okay. And actually, as I mentioned before, we can describe ROC2 graded ring structure of the coefficients of the Burnside Mackey functor, and it is fully determined by the following properties. Firstly, it is strictly commutative. And what do I mean here by strictly commutative? Usually, well, always, if we have a graded ring and we take xy is equal to yx up to some sign, up to some units. And here, in this case, these units, this sign is always trivial, which means that xy is always equal to yx. It doesn't depend on degree. We have 2 elements, A and U. So A is the element already discussed. It is over here. The degree of A is minus sigma. And the second element appearing here is the element U. So U is an element of degree 2 minus 2 sigma. And it has 2 properties, that multiplication by U starting at 2 sigma minus 2, so we are over here, is just transfer our Mackey functor. Multiplication by U starting at 0 is just the restriction in our Mackey functor. And it is isomorphism everywhere else. Just a quick remark where this U is coming from. So we are using here the map HA to HA, the Borel completion. Yes, and this element U is somehow the element which is responsible. So the Borel completion is closely connected to the group cohomology, and the element U is somehow the element describing the two periodicity in the C2 in the group cohomology of C2. So this is usual way how we can describe multiplicative structure. We just need to take a look on the map to the coefficients of the Borel completion. And the third property of the coefficients of the Burnside Mackey functor is that we need to describe how the element of degree sigma behaves after multiplication by A. So we can see that this element after multiplication by A is equal to omega minus 2. So really, this group here is generated by omega minus 2 times A minus 1. Okay. And so I still have some time, right? Even if not, I just have 2 slides more. So using the structure of the Burnside Mackey functor, the ring structure, and the Tate diagram, we can actually describe the multiplicative structure of the coefficients of every green functor. So there are a couple of ingredients of this multiplicative structure. The first ingredient is the module structure over the coefficients of HA. And again, this the action of the coefficients of HA can be described by a couple of elements. Action of A, so this is what we discussed already. The action of U, and here we have a little theorem which says that the action of U can be described in terms of structural maps of our Mackey functor. Of course, this statement is somehow heuristic, but really the action of U can be described. There are 7 different cases in this theorem, depending on where this multiplication starts. So, for example, we've seen that in the Burnside Mackey functor, the coefficients of the Burnside Mackey functor. So multiplication by U starting in the degree 2 sigma minus 2 was the transfer, and the multiplication by U starting at 0 was the restriction. Then we have action of omega. So this is the element coming from the Burnside ring. So this is an element which reflects the graded commutativity rule. The graded commutativity rule for general arrow C2 graded rings is given as here we have xy that is equal to -1 time to the power of the product of fixed degrees times 1 minus omega to the power of the product of twisted degrees, and 1 minus omega is a unit in the Burnside ring. So this is kind of a sign coming from the action of the twisted ring. But here we have a theorem which I more or less mentioned before, is that for any green functor, this ring is strictly commutative, which means that this sign over here is always trivial. So let me just give, oh, not yet. We have 4 more elements which we need to relate to our known elements A and U. So these are elements 1 minus sigma, sigma minus 1, 3 minus 3 sigma, and 3 sigma minus 3. So for example, we have, again, coefficients of the constant Mackey functor on F2. Here we have element U, but we have also element of the degree 1 minus sigma. And we can find a relation of this element to U as being lambda squared is equal to U. So the kind of corollary of all of this stuff is that the ROC2 graded ring structure of the coefficients of any green functor may be determined by this, are determined by these ingredients. So they are determined by being strictly commutative ROC2 graded ring, by the action of the coefficients of the Burnside Mackey functor, and then by relations of these 4 elements to A and U. And I think I will and I should stop here. So thank you very much for your attention. Here we have, okay, thank you very much.
Okay, thank you. Thank you very much, Igor. Okay, any questions for Igor?
So one question. Can you do similar things for CP, maybe for P prime?
Yeah, so this is very fair question, and I think that the answer is somehow impolite. Obviously you can, but I just did it for C2 so far. Because really, what allows us to use this Tate method is very simple subgroup structure of C2. We have trivial subgroup and the full subgroup. And of course, this structure is for all cyclic groups of prime order has this structure. So the answer is yes, it is possible, and I should probably do it at some point. The other thing which I should probably mention is that I think, and also John thinks, that it is possible to do it for cyclic group of orders being powers of 2 or powers of prime order, because this Tate method can be iterated. So let me just quickly mention that these homotopy orbits and homotopy fixed spectral sequence and this, well, bottom row in the Tate diagram works everywhere fine. The problematic bit is the singular spectrum. But because the subgroups of C4 or C2 to the power cyclic group of order 2 to the power I has this linear character, then you can somehow use the method, the Tate square for C2 to compute the coefficients of this singular spectrum. So I think this is like the next step in this, using the Tate method, somehow iterated Tate method for computing these coefficients over C4 or C to the power, cyclic group of power of order 2 to the power I.
Maybe
Thank you.
I can comment that there were some computations involving fixed points of topological Hochschild homology and topological cyclic homology, which also went by first doing the prime order groups and then working one's way up to bigger and bigger prime power orders by means of these sort of Tate squares. So there are slightly, I mean, these are not Mackey functor constructions, but still ordinary graded but equivariant groups that were computed iteratively by this kind of inductive method using the Tate square. So that seems quite promising.
Thank you. Yeah, so these computations, I think these are surely done by Ming-Kong Zheng. And so he computed these coefficients for C4, and Dick Georgakopoulos, so this is a student of Peter May, he did it for IHF2 over C4.
Okay, any other questions for Igor? Okay, so let's thank Igor. Okay, thank you very much.
Thank you very much.